much.
See you in a
Hello,
sec.
JNation. I knew it would be impossible to follow the band, but I hadn't realized it would also be impossible to follow the conference organizers. I work with Roberto. He's not like that in our team meetings. But I think, the good news is I get to talk about the best thing in the world, which is code. And I think we all agree now that programming is rock and roll. Am I right? Yeah. And if you think about it, they've got a lot in common. So, for example, late nights. Maybe doing different things, but late nights. And they all say that programmers are machines for turning coffee into code. So I think we have stimulants in common between rock and roll and programming. And then, of course, there's the swearing. I'm sorry to say this in front of the representative of the City Hall, but both programming and rock and roll involve quite a lot of swearing. Hands up if you've put a comment like this in your code, right? Hands up if you accidentally then committed it and included it in your pull request. Yeah, oops. So, programming is rock and roll. But I'm not actually here to talk about programming. I'm here to talk about efficiency and rock and roll. And when they invited me to do a keynote, I said, fantastic, what would you like me to talk about? And they said, Holly, could you talk about efficiency and rock and roll? And my first thought was, no, actually, I can't talk about efficiency and rock and roll. Those two are very different. Well, let's see. So, like any good comparison, we have to start with a definition. So, efficiency is trying to achieve the largest amount of useful work with as little energy and effort as possible. Okay. Rock and roll is a style of popular music played on electronic... No, that's not rock and roll. We all know rock and roll, it's not about that. Rock and roll is an attitude. But that's kind of hard to define. So let's do it by example. Like a lot of things, you know it when you see it. So let's do an exercise. So I've got a bunch of things, and let's do a thumbs up if they're efficient, and medal if they're rock and roll. Okay, everybody got this? Thumbs up for efficient, medal for rock and roll. Okay, so coolness. Is that efficient or rock and roll? Rock and roll, right? Turning it up to 11. Efficient, rock and roll. Yeah, rock and roll. Yeah. Being productive. Yeah. Being useful. Yeah. Excess. Yeah. And I think probably a lot of you have heard the story of the Van Halen rider. And they used to insist that they would have a bowl of M&Ms backstage, and all of the brown M&Ms had to be taken out. Now this is that is excess, but it's also incredibly wasteful, because someone had to sit there picking the brown M&Ms out. But that's rock and roll, right? Whereas efficiency, on the other hand, it also has to do with waste, but efficiency has to do with minimizing waste. So these are kind of opposites. And then, of course, there's the machine. Efficiency is about the machine. Rock and roll is rage against the machine. So at this point, I'm writing my talk, and I'm starting to get pretty worried, because so far, everything I can think of shows that efficiency and rock and roll are exact opposites. And so if I do a talk called Is Efficiency Rock and Roll, it's going to be a really short and slightly embarrassing talk. But then I started to think about my day job. I work for Red Hat. I'm part of the Quarkus team. And I think probably a lot of you know that Quarkus is massively, massively efficient. But we also like to think that Quarkus is pretty rock and roll. So I've got here the Quarkus World Tour t-shirt from 2022, the last time I was at JNation. And we do a lot of our events as like world tours. And I don't have them with me today, unfortunately, but sometimes you can get the best ever stickers, which are our Quarkus stickers. So, Quarkus shows, I think, that you can be efficient and rock and roll. And then I started to think about it a bit more, and I came up with some other examples. So, for example, queuing. Queuing is an important part of rock and roll. You queue for your tickets. And queuing theory is about efficiency. So, maybe. And then, of course, there's being lazy. I would say that being lazy is very rock and roll. And being lazy is also definitely efficient. What about being a rebel? Is that rock and roll or efficient? Rock and roll, yeah, but we'll come back to that. I think there's a way that it connects to efficiency as well. But this definition of efficiency, of trying to get the maximum amount of value out of the minimum amount of effort, is actually pretty old. It started in the 1700s when people were trying to develop better steam engines, and they couldn't figure out why they put all this fuel into the steam engine and almost no work came out. So the idea with a steam engine and the study of efficiency is that you figure out how much energy you put into your engine, and then at the other end you get energy out, but only some of that energy is useful, and the rest of the energy comes out as waste. And this idea was so good that the business people took it, and they said, well, could we apply this same idea to people? So if we have a process, you put time and money into the process at the one end, and then at the other end, you get out value, hopefully, maybe some of the time. But of course, in any process, there's also waste. And this idea was so good that when we started thinking about programming and how to really write good programs in the 1960s, we took this same idea. So if you have a computer, what you put in is you put in time and electricity and hardware and programmer tears and quite a lot of swearing. And then what you get out the other end is an answer, which is maybe, hopefully, correct, and unfortunately, quite a lot of waste. So really, the idea of efficiency is the idea of how do I minimize the waste that comes out of all the things that I'm doing. And we've had 300 years to practice this, to get good at eliminating waste. So do you think we're very good at it? No. And I first realized our industry had a waste problem when some colleagues told me a story. And this was way back before the cloud. And they had come up with this really cool software that would allow you to provision an instance in 10 minutes. Now this is really boring. Of course, you can provision an instance in 10 minutes, but at the time, this was really exciting. So they sold it to the client, and the client came back and said, but it doesn't work. And what the client was seeing was that it took 3 months to actually provision this instance. We were like, that's kind of weird. We tested the software. It seemed to work. What's going on? When we investigated, we found that there was an 84-step provisioning process. You had to do 84 pre-approvals before you could get your instance. Of course, it took 3 months. And this is, we see this everywhere. So if I want to go to the Zoom landing page, it will take me 18 megabytes of data just to load the Zoom landing page, which is pretty depressing. For GitHub, you saw briefly, even for GitHub, just the GitHub landing page, it's 12 megabytes. We are becoming extremely, extremely inefficient in how we write web pages. So this isn't our imagination either. If you look at the sort of the average size of a web page over time, it's going up and up and up. And somewhere around 2023, we passed the doom point, where a modern web page, the average web page, has more data just to download that web page than the whole first version of Doom. And so if you think about the Doom, Zoom, because this isn't even Zoom. This is the landing page of Zoom. I'm not even doing a video call. I'm just maybe thinking about doing a video call. And that is 5 times heavier than running Doom. And it is clearly not rock and roll to use 5 times more footprint than Doom just to get Zoom. And this really matters. It's not just one of those funny things where you can compare it to Zoom, because it means that modern web actually doesn't work for a lot of people. A while ago, LinkedIn, they had this cool new feature, and so they went to do their user research, and they went to Nashik in India, which is a medium-sized town. And so the user researcher sat down with the person and said, so, let me see you use this feature. What do you think of it? And the user just watched a blank page because it couldn't actually load. The feature was so heavy. And so what this means is that a whole bunch of developers in San Francisco had done all of this work in order to make something that actually was useless for the users, which is it's just stupid, right? And it means that people can't use the hard work. But there's also bigger impacts as well. It's really environmentally destructive to have all of this bloat, to have all of this waste. And all of this code is killing the planet. But then we have another problem. So when we do write the code, it's too big, it's too fat. But then quite often what happens is we write the code, and then we forget about it. We deploy it, and then it just hangs around forever. So we have this really bad zombie problem in our industry where 1/4 of the servers out there aren't doing any useful work. They're just forgotten. And when I say no useful work, I don't mean that they're serving cat pictures. What I mean is that there has no data has gone in or out of that system for the past 6 months. And the average server is running at about 15% utilization. So almost all of its capacity is wasted, which is just stupid. And we have the same problem with data. We have an enormous amount of data waste. 68% of the data that we store never gets used again. The only problem is we don't know which 68%, so we can't delete it. And with all of this, obviously there's a huge financial impact. These servers cost money, and then we don't use them. Storing this data costs money, and then we don't use it. But of course, it costs a lot of electricity as well. And all of that hardware has a carbon footprint. There's an embodied carbon in the carbon footprint. And cooling these data centers takes a lot of water. And then at the end of the life cycle, we have to get rid of these servers, and so then that's e-waste. So this is just pretty terrible. But the good news is that there are things we can do, and they're actually really good things. So one of the things we can do is something that I called light switch ops. And I started talking about light switch ops, and then eventually someone else put light switch ops in a book, which was very exciting for me because I thought leadered. It was the only time, but I thought leadered. So the idea with light switch ops is when we leave a room, we just turn out the light. But with our computer systems, we leave them running all of the time. And the reason we do this is because we know terrible things happen if you turn a computer off and then expect it to turn back on again in the same state. But we can fix this. So let's make our systems so that they're resilient and can tolerate being turned off. And then let's actually turn them off. And if we do that, there's really big savings. So I saw a talk a while ago, and they'd just written a script to turn their servers off outside of business hours. and it saved them 30% of their cloud bill. This is a big amount of money. Or now we're starting to see, if you don't want to write a script because you don't want to use bash, or because you don't want to use cron, which I understand, because nobody can get the cron syntax right, now we're starting to see tools that can do this as well. So there's a tool called Daily Clean from AXA France that just gives you a UI, so you can sort of set it up to turn things off. But even with these tools, probably a lot of us don't turn computers off. And there's a couple of reasons for this, I think. The first is forgetfulness. We set something up, and then we forget it. I did this when I was learning Kubernetes. I provisioned a cluster, and then I forgot it for 2 months, and then I realized I'd provisioned a cluster that was €1,000 a month, and it had just been there doing nothing at all. So that was a slightly awkward conversation with my boss. But then as well, often we don't turn them off just because we don't care. We can't be bothered. And then the final reason that a lot of us don't turn these systems off is fear. It's risk aversion. We're not sure if the system's maybe the system is important, and there's a lot of bureaucracy to be able to turn it off, and so we're just a bit worried. And this is where I think the spirit of rock and roll comes in again. We need to be a bit braver when it comes to things like making a difference. We need to be brave enough to make a difference and turn servers off. Because the difference it makes, there's the money, but then, there's the environment, there's all of that. And then as a bonus, if you can prove that you can turn your system off and on again, you're testing your disaster recovery, which is a win. There's another thing that we can do to reduce waste, which is just to write faster code. And I call this the vroom model. And I didn't really think about SEO or naming or anything when I called this the vroom model, and I hadn't thought to type it into Google when I called it the vroom model. Because if I had, I would have realized that there is already something called a vroom model. And the vroom model was invented by Dr. Vroom. It hadn't occurred to me when I called something the vroom model that there was a Dr. Vroom who had invented a model. But my name was actually worse than that, because I didn't call it the vroom model spelled the normal way. I called it the vroom model with lots of R's and O's, and it's a non-determinate number. The SEO of something with an indeterminate spelling is very, very poor. And so if you search for the vroom model with all of the R's and O's, what you get isn't Dr. Vroom's model. What you get is a whole bunch of pictures of cars and women wearing not very many clothes. So you can see I've put the banner there to make it okay for the representative of the city of Coimbra. This was not so good. So naming is the hardest problem in computer science, but my vroom model, what it is, it was inspired by looking at this paper that did the rounds a few years ago. And I think everybody loved looking at this paper, because what it did is it compared the efficiency of various programming languages. And no matter what your language of choice was, unless your language of choice was like Python or PHP or Perl, you could find some other language that was worse than you, and then you could laugh at them and tell them that you were better. And that's how programming works, right? It's all about laughing at other people. But what I noticed in this paper is that they have two columns. They have a column of how much energy the program uses, and a column for how much time it uses. And those two columns were almost the same. So I plotted it to be sure, and you can see that that trend line is almost straight. And you can also see, I'm a Java developer, so you can see that Java is really quite efficient, which I like. If you're a JavaScript developer, people are probably laughing at how inefficient your code is, but you can point out that actually, you're pretty okay. You're number 13 on that table. There's a lot of languages that are much, much worse than you. But I want to give you now an example of the vroom model in action. Coming back to my day job, which is Quarkus, which is very efficient. In the distant, distant past, it used to be that Java frameworks were optimized for dynamism. You could change the engine of the plane while the plane was flying. This was very clever engineering. But now, you do not ever need to swap out a dependency of your application while your application is actually running, because we have CI/CD. If you don't like your build, you just get a new one. You just run it through the CI/CD pipeline. You do not need to SSH into production and patch it. Hands up if you are SSHing into production and patching. No hands, that's good. Oh, I think I saw one hand at the back. You should not be doing this. You should be using CI/CD. We have CI/CD for a reason. It means that if you don't like your application, you just get a new one. Cloud applications, all applications, should be immutable. And yet we have all of this infrastructure for dynamism built into the language. That is a tax that gives you no benefit, because a highly dynamic environment in a container, it's just totally pointless. And you can see, like, Java does a lot of stuff to support that dynamism. So for example, when a Java framework starts, the first thing that you do is you build it, and then you think you're done, but actually all you've done there is just a bit of packaging. And then when you start your application, a whole bunch of stuff happens. So you have to load all your config files, you have to read all your YAML, you have to then build a meta model of the world, and you do your class path scanning, and then finally you have this meta model, and then you start your thread pools, and you initialize your I/O, and then eventually you're ready to start work. And at this point, the JavaScript people in the room are looking at the Java people going, that seems really silly. Why are you doing all that? Why don't you just be more like JavaScript? And the really bad thing is if we start the application more than once, we have to do all of that work every single time. There's no record of it. There's no memory. And this really affects what goes on in the application. So for example, if you're using Hibernate, Hibernate will try and automatically bind to your transaction provider. So it will use Java Reflection to load the transaction provider. If it doesn't find the most popular one, it will look for the second most popular one. If it doesn't find that one, it will keep going. If it doesn't find that one, it will keep going until it gets to the most obscure transaction provider it knows about. It will do this. If it can't find it, it will try 129 times to load a transaction provider before it gives up. And it will do that every single start, even though the application did not change. A new transaction provider did not magically appear between when you last ran it and this time because you're running in a container. So that affects startup, but it also affects what happens at runtime. So for example, if you want to dispatch to a method, what the JVM will do is it will look at every possible implementation before finally hooking up to the right one. And that takes time. This is what's called megamorphic dispatching. If, on the other hand, you only have one possible implementation, you can do what's called monomorphic dispatching, which is a lot cheaper. And again, the JavaScript people are looking at this going, why don't you just use tree shaking like JavaScript does? Well, that's more or less what Quarkus did. Because what Quarkus said is, what if, instead of doing all of that initialization at runtime, what if we just did it at build time instead? So we move all of that stuff that doesn't change and only do it once. And what that means is that if you start the application multiple times, it's efficient because you're not repeating the work. And it also means that your throughput of your application is higher because you're not carrying around all this reflection and you're not carrying around all this crap that you didn't even need. And you can see the impact of this, and you can see how it relates back to the vroom model if you look at the performance numbers for Quarkus. So I've got here some measurements that we did where we looked at Quarkus and we looked at legacy frameworks, and we compared the throughput and the energy used. And you can see that on this graph, the shorter line means a lower maximum throughput. So with the legacy native, it couldn't, it took about 7,000 requests per second, and then it just couldn't take any more requests. So that shorter line is a lower throughput. Whereas with Quarkus on JVM, it has this really high throughput. And the higher lines means a higher energy usage. So what you want is that long, low line. And you can see that everything that is short is also higher. And Quarkus on JVM has the highest throughput, and it also has the lowest energy usage. And so this is exactly the vroom model in action. It's showing that if you make your code faster, it is going to be more efficient, and it is going to save the world, which is cool. So I think we often think that there's this trade-off, when we're doing performance tuning, that I can either, optimize my startup time, or I can optimize my throughput. But what that graph shows is that at least some of the time, that's not actually the trade-off. You will be able to optimize both, which is a double win. It's really cool. So this is a seesaw folded in half. And you may think, oh, well, yeah, okay, but that's not actually realistic. And seesaws don't actually fold in half. It turns out you can buy a seesaw that folds in half. And there's another trade-off that we beat as well, which is quite often when you think about really efficient programming languages, really efficient programming models, they're a bit user hostile. So for example, going back to the programming language comparison, Rust, very, very efficient, not the easiest language. And what I love about this Quarkus example is it shows that you don't have to make life hard for yourself. You don't have to go and start using Rust in order to become efficient. There are things that we can do to get rid of waste without worsening the user experience. And it's actually more than that. We can get rid of the waste and make the user experience better. So with Quarkus, we have this really high machine efficiency, but we also have this great human efficiency. It is a productive environment to program in. So for example, with Quarkus, there's a whole bunch of boilerplate code that you get in a normal Java programming model that we just got rid of. And with Quarkus, you get live coding out of the box. So you do Maven Quarkus dev, and then all of your changes are instantly reloaded, and your tests are rerun as well, which is really, really cool. And again, the JavaScript people are thinking, well, wait a minute, we've had live coding for ages. Why is this interesting? But this is interesting. This is cool. And so this is what we really try and go for with Quarkus is this idea of developer joy, of making people more efficient because they are happier when that happens. And this is a double win. So I've talked a lot about Quarkus and a lot about Java, and I know not everybody here is a Java person, but I think the principles are really general. That's what I want you to take away, is this idea that if you just have that rock and roll rebellion and challenge some of the assumptions about how things are always done in your ecosystem, you might be able to find really big bits of waste that you can just get rid of. Now, of course, it's not 2025 if a conference doesn't mention AI. And I think this idea of trying to make a programming model more concise, of trying to make a programming model better, I think some people are now saying, oh, well, but programming is dead, and it doesn't even matter if the language is bloated, because we're going to have the computer do all of the typing. I think this idea is really, really wrong. And I think there is a risk that we have with some of the AI coding assistants and the ways that we're using them now. Because AI coding assistants give too much weight to the past. And they also really, really like typing. And so a while ago, I used ChatGPT to generate a sample Quarkus application. And it started typing, and I was really pleased at how much work it was saving me. And then it carried on typing, and I was a bit concerned, and it carried on typing, and I was more concerned, and it carried on typing. And I looked at what it had produced, and it produced so much code. But 70% of the code that it produced was completely useless. It didn't do any harm, but it wasn't necessary. But it was like the AI was being paid on lines of code, which is a really foolish thing to pay anybody on, including an AI. And so what it had done was it had just created all of this stuff in my code base. And we spend a fairly small amount of our work life writing code and typing code. We spend much more time reading code. And so if you have an inefficient programming model, or you take your efficient programming model like Quarkus, and then you have an AI write really flabby code, even though it could write concise code, and then it comments all of the getters and it comments all of the setters, what you're doing is you're shifting the work to future you. You're not actually saving time. You're just having this illusion of saving time. And I think we need to be careful of this. There are really good ways to use AI coding assistance. I think generating code is maybe not one of them. I think generating code is something that we need to be cautious of. But it's so easy to fall into this trap. It's so easy to look at something and say, oh, look, it's made me so much more efficient, when actually it's done the opposite. I saw this on social media a while ago, and someone said, this is VC culture. And I just heard of a founder who monitors his co-founders and employees' productivity via a Whoop group. The team is collectively averaging 5.5 hours of sleep per night. Now, on the one hand, this is very rock and roll. This is showing a great deal of commitment. But on the other hand, if you are working tired, that is equivalent to working while drunk. Your decision-making is bad. You make mistakes. And I don't think anybody would say, my colleagues have come into work drunk. That's great, we're going to achieve a lot today, right? But somehow there's this idea that if people are like depriving themselves of sleep to code, it's going to be better. And we all know that that's not actually the case, or we should all know that that's the case. And so I hoped that that's what this was going to say, was I told them to go and get some sleep. But it didn't say this. Instead, it said, if you haven't implemented this kind of monitoring at your company, I suggest you do it. No, this is a bad idea. Don't do this. Because even for machines, you can't actually get 100% efficiency. Even for machines, you can't just like squeeze more work out by driving the system harder. And again, this is something that we should have learned 300 years ago. So when they started making steam engines and trying to figure out why there was so much waste, they invented thermodynamics. And thermodynamics tells us that there is a maximum limit to how much energy you can get out of an engine. And it's a lot lower than you think. So with a modern car, the theoretical limit of how energy efficient it can be with an internal combustion engine is about 37%. That is really low. That means 2/3 of the energy that you put into your car is just getting thrown away. But modern cars don't run at 37% efficiency. They actually run at something more like 20% efficiency. Why is this? Is it because they couldn't be bothered to make the car efficient? No, It's because if you run a car at 37% efficiency, the engine wears out really quickly. So they deliberately detune the engine in order to make the car last longer. And so the maximum efficiency isn't actually necessarily the best thing. And you can see this everywhere. So if you have a stool, for example, a three-legged stool is extremely efficient. It has the optimum number of legs to be stable. If you look at a dog has more legs than is strictly necessary. And you can test this, because if you remove the leg from a dog, obviously don't try this at home, if the dog has an unfortunate accident, it is still a perfectly functional dog. It will go to the park and sniff other dogs and do all of the doggy things. If you remove the leg from a stool, that is no longer a functional stool. That is firewood. So there's a trade-off there between the resiliency and the efficiency, and the resiliency lowers efficiency, but we really want the resiliency anyway. And it is exactly the same for people. That if you work too hard, it seems like you're being efficient, but actually you're lowering the resiliency of the system, and you're not even becoming that efficient. And I think we've all seen this. So, a lot of us have had a colleague who's just working that bit too hard, and you ask them to do something, and they just bite your head off, and it comes back to the swearing. That they get really angry, and you just ask them to do something, but it's because they're so stressed. And so we really do need to relearn the value of slack. And I should clarify here that when I say the value of slack, I do not mean that slack. That slack is a human hamster wheel system. We do not need to be relearning the value of that slack. And I think, once again, it shows that naming is the hardest problem in computer science. When I say the value of slack, I mean the value of just doing nothing. Because if we do nothing, we can actually achieve more. And this is something that we see in machines, and we can actually measure it as well. There is a part of your brain that when you are doing nothing, it becomes more active. And that part of the brain is what's involved in problem solving. And so this is why so many of us will have our best ideas in the shower. And apparently, 72% of people have their best ideas in the shower, and 14% of people specifically have showers for the purpose of coming up with ideas. I should say this research was sponsored by a shower company, so, but I think it's true, right? This is something that we've all seen. And again, we can see this physically in, with those psychological measurements, but we can also confirm it with the math, because queuing theory is about modeling what happens in systems where there's work waiting. And I don't have time to do a full queuing theory course, but the basic idea with queuing theory is that you model what happens, and then you can make predictions. So you have an arrival process, and then you have a queue, and then you have some servers, and then eventually you get completed work, which is awesome. And if you have too few servers, you get these queues building up, and people are unhappy. And queues build up really, really quickly. So if you go from 80% to 90% utilization in your system, your wait times double. If you go above 90%, your wait times become almost infinite. So you have this really big delay cost. But of course, you need to balance that against the fact that the servers have a cost as well. So it's about that trade-off. But what we can see is that doing a little bit less actually may give you better results and better productivity. It used to be that the 6-day working week was standard, and Henry Ford had the bright idea of moving it to a 5-day week, and productivity actually stayed the same. He made more money by having his employees work less. And we can see the same again if we go to a 4-day work week. It sounds absolutely ridiculous, but studies find that retention is better, and revenue is higher as well. So there's this idea of Jevons paradox, which is that if you increase efficiency, actually, you don't really get it back. And if you widen a highway, you think you're going to have really easy journeys, and you actually just get more cars on the highway. And so we can reverse this, and we can say, we narrow the highway, and we actually get more done. I want to finish very quickly by sharing the most inefficient thing I've ever done, which is there's a language called Rockstar. And Rockstar allows you to write programs that look like heavy metal ballads. And it was written in JavaScript, and I decided I needed a Java version of it. So I wrote a Quarkus extension that allowed you to live code Rockstar ballads. It took me a month. It was not valuable. And I gave a talk on it. And someone left the talk, and the feedback was, I do not know what Rockstar was, but I don't think I'm going to be using it in my job. Of course you're not going to be using it in your job. The programs are heavy metal ballads. But the value of the talk, I thought, but definitely the value for me of doing it wasn't because you could take it away and use it at work. It was because we learned so much by doing this. We learned so much by sort of leaning into the silliness. And so I really would encourage you to embrace the play, because so much good comes from play, and so much efficiency actually comes from play. So, to wrap up, too long didn't pay attention. Rage against the waste. Our planet deserves better. Waste is just stupid. If you work less, you may surprise yourself by achieving more. But happiness, so get rid of the waste, but happiness is not waste, and idleness is not waste. And look for double wins everywhere, because they're there. You don't have to give things up. You can find the double win. And with that, thank you very much. The slides are there, and I'll see you around.